Okay, morning everybody. Okay, today's topic will be on practical electricity. This topic generally evolve around the usage of electricity. Example, the time of the common users of electricity and costing of electricity. How do we calculate electricity? How much do we need to pay? And after that, we also will be touching base on the hazard of electricity, and eventually we'll end it off with the possible precautions of using electricity. Okay, without talking too much, okay, we will start the lesson proper. Okay, we'll look at the first section here, which is uh, the users of electricity. Okay, now electricity, the first users that we look at will be the very, very common one, what we know as the electric heating, the heating effect of electricity. In general, most of the heating effect always revolve around the use of heating elements. For example, like your electric heater, iron, your radiators, and even hot plates. Sometimes as common as using your electric heater, instant heater. Okay, they all uses these heating elements whereby we actually make use of electrical energy. Then after that, converted it to your heat energy. Okay, so we look at this type of conversion. Okay, now and most of the heating elements in the market actually uses a common material, which is what we know as nichrome. When we uses nichrome because one of the main reasons is because nichrome is one of the material that has high resistivity, and because it has high resistivity, the resistance of the material is very high. Okay, and because the resistance is very high, is able to heat up very, very fast. Okay, so he's able to heat up rapidly, and as a result, he's able to generate heat at a very, very short in time interval. And of course, one of the most important thing that we have is also because has a high melting point, so it will not melt easily. And thus I can use it for heating element. Same thing, the formula I listed on the right side here is to bring your attention to here. Okay, when we look at high resistivity, when do I use this word high resistivity? It's in the previous topic when I look at resistance. Okay, high resistivity, if everything remain constant, if I have high resistivity, means my resistance of the material will be very high. Okay, so that's why we usually opt for the use of nichrome, okay, because it has high resistivity. Other possible uses, okay, can be electric, it can be light energy, it can be even like sound energy that we use in speaker. Okay, but heat energy is one of the common thing that we actually talk about in your electricity. Okay, now for calculating of electricity, the formula that we use is the one that we see quite often. Your power equal to work over time, which is energy divided by time. Okay, but in electricity, we have another way of calculating whereby we look at is voltage and current. Okay, so if you look at your kinematics, you look at your dynamics, all these things. Yes, power, the common energy we have is work per unit time, amount of energy used per unit time to do work. For electricity, it's also the same thing, but because electricity we generally talk about voltage and current, so that's why we want to regroup the formula for electricity in term for power to relate current and potential difference into the formula. So that's why we have the secondary formula appearing. Okay, for this session wise, I will not dwell too much on the derivation. How do I derive work over time to voltage, product of voltage and potential difference and current. Okay, if you need to, okay, you can look up the internet or even your textbook. They actually provide some simple proving. Okay, and one thing I like to highlight is using this formula and Ohm's law, V equal IR, I can actually get another two variations, permutations of the formula. So other than P equal to IV, I can actually have V squared over R, or I can have P equal to I squared R. These three formulas are talking about the same thing, which is the power of the appliances. Okay, but they are all in the various permutations. For example, I will use V over I in the for my question if the question doesn't give me resistance. Okay, if I use I square over R, maybe I will use it because the question doesn't have potential difference, so I will actually use I square R straight away. It's more immediate. Okay, and the same as dynamics energy section, the unit for power is still under watts. Okay, not much difference. Okay, now electrical energy, one thing to take note is that in terms of calculating your bills, the SI unit for energy is joules. But it's just that in terms of calculations, okay, in terms of the presentation, if you leave energy in joules, if you look at the calculations, okay, for your energy usage, electrical energy usage in joules, you'll find that the numbers generated, let's say for example, a simple use of a laptop for maybe 2 hours, 3 hours, I can actually easily clock maybe how much electrical energy it could be like 1 megajoules, which is like 1 million joules. So the number is actually quite big. Okay, so because of the way that we present the data is like it's quite cumbersome, it's quite long. So what we have is we actually derive a new unit for energy. Okay, in terms for just for calculation of electricity, we term it kilowatt hour. Okay, for kilowatt hour here, how do we derive this? Is we actually uses the formula. Okay, same thing. Okay, if I want the energy to be in joules, remember in physics, all your variable must be in SI unit. For power, the SI unit for power is in watts. Okay, the SI unit for time will be in second. So if you substitute SI unit into the variable, the answer that you get for energy will be also be in SI unit, which is joules. Okay, the other variation that we have is I purposely, okay, convert my power to be kilowatts. Okay, and I purposely leave my time in kilowatt hour. Okay, so if I do that, when the product of power and time in kilowatt and hour respectively, I will find that the unit for energy will now be kilowatt hour. Okay, like I mentioned before, the reason why I use kilowatt hour for electrical energy is because of the ease of calculation. So when I use kilowatt hour, the number I generate for, let's say, for the use of electricity, my electricity, instead of giving me 1 million joules, 10,000 joules, maybe 2 million joules, I actually get a more realistic number, like maybe 2 kilowatt hour, 3 kilowatt hour, or 0.45 kilowatt hour. The number makes more sense to like maybe to everybody or to layman people. Okay, small appliances uses small energy, big appliances uses big energy. So the number makes more sense to the general public. Okay, so that's why we actually want the calculation of energy, electrical energy is to be exact, to be in kilowatt hour. Okay, so this is the one that I mentioned. Okay, the conversion. So because energy is power times time. Okay, so if I substitute power is P equal IV, I will get IVT. And same thing because power energy is power divided by time. Time, correct? If I substitute power V square over R, I will get various permutation of energy. Okay, for formulas for the energy. So I will get V square TR or even I square RT. So it depends on how you permute the formula. So example, I square R, if I substitute energy is power times time, the power I will substitute inside here, I will get I square RT. So these are actually two formulas that we are looking for. Actually one formula we are looking for. It all started with power equal energy over time, or sometimes we like to include power is equal to IV. And of course, sometimes the common formula that we have at the previous two topic is V square over V equal IR, your Ohm's law. Okay, so when you combine these few formulas together, you get actually a list of other formulas that you can actually use it quite freely. Okay, so just to take note of it, when you look at it as solving the mathematics behind electrical energy. Okay, now for calculation, the guy who actually keep track of the amount of energy we use, okay, we are not going to do my calculation, press my calculator to identify how much energy I use. We have this meter, we have this electrical meter outside our house. This electrical meter here actually is responsible for documenting or recording how much energy I use. Okay, and it's usually measured in kilowatt hour already. Okay, it's actually measured in kilowatt hour. Okay, so here I give you an example of how conversion of kilowatt hour and joules. Okay, so remember they all use the same formula, energy equal to power times time. The only difference is if I need joules, my power has to be in watts. Okay, my time has to be in seconds. So let's say I do a simple calculation. I want to calculate the energy I use for 1 kilowatt of item. It could be maybe hair dryer if I use it for 1 hour. Okay, if not hair dryer, it could be maybe my laptop. Okay, I use my laptop 1 kilowatt hour for 1 hour. So I want to calculate how much energy I use. Okay, so this is the power. This is the time. Okay, so if I leave it in SI unit, 1 kilowatt 1 kilowatt will be 1000 watt. 1 hour will be 3600 seconds. So if I do a product of these two, I will find that for my energy, okay, it will be 36. I will have 50 at the back. Okay, this will be the energy I need to maybe for use on my laptop in 1 hour. Just 1 hour only, I'll get actually this chunk of numbers, which is I get a 7-digit numbers. Okay, but what happens if I convert it to kilowatt hour? I purposely set power to be in kilowatt. Okay, I choose this unit, and time I purposely set it to be hour. Okay, and the product of these two, I will still get energy. Okay, but it's actually presented as 1 kilowatt hour. Both information represent the same thing, the usage, the energy used for a 1 kilowatt appliances for 1 hour. But just that the representation of the numbers is quite different. Okay, for example, it's 3.6 million versus 1 kilowatt hour. So 3.6 million joules is like inherently to everybody, it's like a big number. So that's like, but the number, the energy I use is actually maybe 1000 watt is maybe like a laptop for 1 hour. So by incur 3.6 million joules, so it's like a bit daunting, a bit scary if I present this information. Okay, so it tends to have like misinterpretations. So that's why I purposely set the unit to be kilowatt, the power to be kilowatt, and the time to be hour, so that the energy now is measured in kilowatt hour. So small appliances, small amount of money, small amount of energy being used. Okay, so usually what we have here is once I get the electrical energy, let's say example I uses 149 kilowatt hour. Okay, so I will look at the rate. Here the rate here refer to 27 cents for 1 kilowatt. Okay, so this is how the presentation works. Okay, so when we talk about the rate, the how much costing for electrical energy, the costing for electrical energy is always given in kilowatt hour. It's always given. So how do you get the total amount? $40.65. I'll just multiply these two. Okay, because I know 1 kilowatt hour is 27 cents. So 149 kilowatt will be a simple rate ratio formula for the like primary school mathematics. I'll just multiply them. I'll get 40.65. Okay, so this is how we look at your electricity bill, how we charge. Okay. Now, the last question here that we look at is how do we look at certain items like your presentation of certain rating. For example, your light bulb is 60 watts, okay, 240. Now, if it's a 240 watts light bulb, okay, but now what I do is I attach this light bulb to 120 watts, 120 volts power source. Okay, so at 60 watts, okay, the voltage rating is 60 watts at 240 volts. So how do I calculate the current through it? Okay, so here same thing. Now remember the rating here is based on 240, but you are charged at you are powered using 120 volts. So there is a disparity among the users. Okay, now just to take note is that 240 volts gives me 600 watts. Does it mean that 120 volts will give me 30 watts? Okay, it may or may not. So sometimes it's proportion, yes, for certain equipment, sometimes it's not. So to play safe, okay, always look for, go back to the basic, okay, regardless of the power source, okay, okay, the rating plays a part. Example, 240 give you 60 watts. So it means that at 120 watts, the power of the lamp is confirmed not 60 watts. Okay, so based on the specs here, okay, is 240 volts, I will give 60 watts. Okay, only at this number, only at this rating, 240 volts. So if you use 120, it will not be 60 volts. So this solution is out. Same thing, you cannot, based on the specs, okay, you cannot use 240 volts because the power source that they give in the question is 120 volts. So you cannot just change the power source this way. So go back to basic. Here is always go back to the basic. Look for the characteristic of this light bulb here. Okay, between at 240 volts at 60 watts, at 120 volts, what is the power here? Or what is the rating here? Okay, the only thing that is common between these two is they are using the same light bulb, which means the characteristics of the light bulb is the same, which means that the characteristic we are talking about is the resistance of the light bulb is always the same, whether I use 240 volts or 120 volts. So the first step that you do is based on the specs here, you actually should work out the resistance, okay, the specs of the light bulb, because the same resistance will be used, okay, because the same light bulb is being used when I am 120 volts setting. Okay, so here what we are looking out for is to identify what do you mean by rating. What when the question give you rating, how do you use it? Okay, so the correct approach that you look at is always look at the resistance of the appliances. Identify the resistance of the appliances, which is the base thing that never change, okay, regardless of what power source you use, if it's a 240 volt or even 120 volts. Okay, so just take note of this. Okay, so this question here, okay, where the important thing is to encourage students to look at the question carefully, analyze them, don't just use the math and just plug it inside the formula straight away. Okay, now so just take note of this question. If there's some ambiguity, so remember to scroll back to the previous few slides and to relook at the example again. Okay, if not, okay, this is where I end off, okay, for this first part of the topic. Okay, any questions, any comments, any improvement that I need to do, okay, please leave your comments at the bottom there. Okay, if not, okay, remember to subscribe to my channel, okay, and to get the latest update on the topics or the videos that I will be using to get an update on it. Okay, if not, thank you very much. Bye bye.